Right now, in a tunnel in Louisiana and in another one in Washington state, a laser beam is being watched more closely than almost anything on Earth. As you sit here, that beam is holding steady across a pair of tunnels, each 4 kilometers long. It is waiting for the fabric of space itself to twitch. And every few days, it does. Because right now, black holes are colliding across the universe. They are billions of light years away. You will never see them. But you can feel them. When 2 black holes crash together, they send a ripple through space and time. And that ripple, faint almost beyond belief, is washing over your body at this very second. In the past few weeks, scientists released the largest catalog of these collisions ever assembled. 161 brand new black hole crashes, announced at once, a running total of 390. And hidden inside the data, 2 black holes that, by the old rules, should not even exist. In the next half hour, I am going to show you how we learned to hear the universe, and I'm going to show you exactly what it just told us. Let me start with what scientists actually announced, because the scale of it is hard to hold in your head. A collaboration of observatories on 3 continents just published the biggest gravitational wave catalog in history. Gravitational waves are ripples in space and time. I will explain exactly what that means in a moment. This new release added 161 fresh detections in a single batch. Before this, the running total had been climbing slowly for a decade. Now it stands at 390 confirmed events. Almost all of them are black holes colliding. A handful involve neutron stars, the crushed cores of dead stars. The observatories behind this are called LIGO, Virgo, and CAGRA. Together they form one team spread across the United States, Italy, and Japan. Scientists call the group the LVK collaboration. I will just call them the listeners, because that is what they built. Not a telescope that sees light, a machine that feels the universe move, and here's the part that should stop you. During their observing runs, they now catch a new collision 3 or 4 times every week. A decade ago, we had never caught a single one. Now the universe barely goes quiet. So what exactly are these ripples? And why did it take humanity 100 years to catch them? To understand this catalog, you have to understand one strange idea from Albert Einstein. Just over 100 years ago, Einstein finished his theory of gravity. He called it general relativity. Before him, people pictured space as an empty stage. Things simply sat inside it. Einstein said something far stranger. Space and time are woven together into a single fabric. He called it space-time. And that fabric can bend, stretch, and ripple. Anything with mass presses into this fabric like a heavy ball resting on a stretched sheet. That dent is what we feel as gravity. The Earth is not pulling you with an invisible rope. You're sliding along a curve in space-time that the Earth's mass created. That is gravity. Here is a way to picture it. Stretch a rubber sheet tight and roll a marble across it. On a flat sheet, the marble runs straight. Now set a bowling ball in the middle. The sheet sags into a bowl. Roll the marble again, and it curves toward the ball. No force reached out and grabbed it. The marble simply followed the bent surface. That is what the planets do around the sun. They roll along a valley carved into space-time. Now, in 1916, Einstein realized something else. If you shake a heavy mass hard enough, the fabric shakes too. The dent moves and it sends out waves, ripples in space-time itself, spreading at the speed of light. He called them gravitational waves. But then Einstein did something revealing. He doubted they could ever be measured. The effect was so tiny, he believed, that no instrument would ever feel it. For nearly a century, he looked right. The wave stayed a beautiful piece of mathematics and nothing more. So how do you catch a ripple that even Einstein thought was too faint to find? The answer is one of the most extreme machines ever built. It is called an interferometer. The idea is simple to say and almost impossible to do. You measure a length using light. At LIGO, engineers dug 2 tunnels that meet in the shape of a giant letter L. Each arm runs 4 kilometers long. That is about 2.5 miles in a perfectly straight line. A powerful laser is split in 2. One half races down each arm, bounces off a mirror, and returns. Normally, the 2 beams come back in perfect step. Nothing happens. The detector stays dark, but when a gravitational wave passes through, it stretches one arm and squeezes the other. For a fraction of a second, one path grows slightly longer. The beams fall out of step. A signal appears. Now hold on to how small this stretch is. The wave changes the arm's length by a tiny fraction of the width of a proton. Not a fraction of an atom, a fraction of a proton, one of the specks buried inside an atom. One scientist on the team, Dr. Daniel Williams, put it plainly. The detectors, he said, can sense a shift smaller than an atomic nucleus. To feel something that small, you have to silence everything else. A passing truck can shake the detector. So can ocean waves crashing on a distant coast. Even the faint hum of the Earth itself registers. Engineers hang the mirrors on delicate glass threads and float them in near total isolation. They also calm the light with a quantum trick called squeezing. It quiets the tiny jitter that the laser itself carries. Only then can a black hole's whisper stand out. And from that shift, they pull out the story of two black holes billions of light years away. There's not just one of these machines. There are several, spread around the planet on purpose. 2 LIGO detectors sit in the United States. Virgo listens in Italy. Kagra waits inside a mountain in Japan. Spreading them out lets scientists cross-check every signal and roughly triangulate where it came from. The machines were ready, the mathematics was a century old, and then, one morning in 2015, it finally happened. On the 14th of September 2015, the detectors had barely finished a major upgrade. They had not even officially started their first run. And a wave arrived. It hit the Louisiana detector first. 7/1000ths of a second later, it reached the one in Washington state. That gap is exactly what you would expect from a wave sweeping across the Earth at the speed of light. When scientists cleaned up the signal, they found a shape they had only ever seen in theory. 2 black holes locked in a death spiral, whipping around each other faster and faster. One weighed about 36 times the mass of our sun, the other about 29 times. In their final moment, they merged into a single black hole roughly 62 times the sun's mass. If you are doing the math, some of that mass is missing. About 3 suns worth simply vanished. It did not really vanish. It was converted into pure energy, poured out as gravitational waves in a fraction of a second. For that instant, this one collision released more power than every star in the visible universe combined. Not in light, in gravity. And it happened 1.3 billion light years away. The ripple traveled for more than 1 billion years to reach us. When the team turned that signal into sound, it made a soft, rising note. Scientists call it a chirp. The universe, for the first time, had spoken in a language we could finally hear. The discovery was announced to the world on the 11th of February 2016. Scientists who had spent their whole careers chasing this moment wept at the press conference. 2 years later, 3 of the physicists behind LIGO were awarded the Nobel Prize. It was the payoff for an idea that had waited a full century for proof. That was one collision. This new catalog holds 390. So what actually happens when 2 black holes meet? Let me slow down and show you what these signals are truly recording. A black hole is a place where matter has collapsed so completely that gravity wins entirely. Nothing escapes it. Not gas, not light, not information. There is only a boundary called the event horizon. Cross that boundary and there is no path back out. That is the definition of a black hole. Now imagine 2 of them orbiting each other, locked together by their own immense gravity. As they circle, they stir the fabric of space-time and bleed energy away as gravitational waves. Losing energy, they fall closer. Falling closer, they speed up. Speeding up, they lose energy faster still. It is a spiral with only one ending. Over millions of years, the orbit tightens into a blur. In the final second, they are whirling around each other hundreds of times at a large fraction of light speed. Then, the 2 event horizons touch and swallow each other whole. That is the merger. The new, larger black hole is left wobbling like a struck bell. Scientists call this the ring down. It shudders, sheds its last waves, and settles into a smooth, silent sphere. The collision is over. It helps to picture the 2 black holes as 2 hands stirring a bathtub. At first, they make gentle waves. As they speed up, the waves grow taller and come faster. At the very end, the water erupts. Then, suddenly, it goes still. All of that plays out in the wave that reaches our detectors. The rising pitch is the spiral. The peak is the crash. The fading tone is the ring down. Scientists can read that whole life story from a single second of signal. The whole event, the part our detectors can hear, often lasts less than a single second. In that second, more power is released than by every star in the cosmos shining at once. And now we have heard that exact sequence 390 times, each one a private catastrophe, billions of years old. But this latest batch did not come from a single lucky night. It came from a marathon. The 161 new collisions all came from one long stretch of listening. Scientists call it the 4th observing run. This release covers the second half of it. The detectors recorded these signals between April of 2024 and the end of January 2025. 10 months, roughly 300 days of holding those laser beams steady and waiting. During that stretch, the machines were more sensitive than they had ever been. Better mirrors, quieter lasers, and clever quantum tricks let them hear deeper into the universe than before. The farther they can hear, the more collisions fall within reach, and they came pouring in. 3 or 4 confident detections, week after week, for months on end. This run was also special because Virgo, in Italy, was fully back in the network. With 3 or more detectors listening at once, scientists can pin down where a signal came from. The full findings were published in the Astrophysical Journal and its companion, the Astrophysical Journal Letters. These are not press releases. They are peer-reviewed papers, checked by other scientists before release. It is worth pausing on that detection rate. 3 or 4 a week does not sound dramatic. But remember, each event is a pair of black holes destroying each other. A generation ago, we did not know such collisions happened at all. Now they are so routine that scientists have to sort through them in bulk. The universe, it turns out, is not a quiet place. It is a crowded, violent, endlessly ringing space. The team is careful with its language, too. Not every blip is called a detection. Each candidate is rated by how likely it is to be a real cosmic event, rather than noise. Only the confident ones make the headline count. The rest are flagged, honestly, as uncertain. But buried inside those 161 signals were a few that broke records outright. One signal in this catalog stands above all the others. It arrived on the 14th of January, 2025. It is, quite simply, the clearest gravitational wave humanity has ever recorded. It came through about 3 times louder than that historic first detection back in 2015. The 2 black holes were closely matched, around 32 and 34 times the mass of the Sun. They merged more than 1 billion light years away, and the signal arrived almost perfectly clean. That clarity let scientists do something they had only dreamed about. They studied the ringing of the final black hole. Remember the ring down, the wobble right after the merger. A black hole rings at specific tones, like a bell. From this one signal, the team measured not 1 but 3 separate notes in that ringing. Each note carries information about the black hole's mass and its spin. Reading those tones is a brand new field. Scientists call it black hole spectroscopy. It is the closest thing we have to taking a black hole's fingerprint from billions of light years away, and the tones matched what Einstein's equations predicted, right down to the fine detail. This is what scientists mean when they say the signal was loud. It was not loud like a sound in your ears. It was loud in clarity, so little noise, so clean a waveform that they could take the black hole apart mathematically. But the same clear signal let the team test something even deeper, an idea from Stephen Hawking. Back in 1971, Stephen Hawking made a bold prediction about black holes. He said the surface area of a black hole's event horizon can never shrink. It can stay the same. It can grow, but it can never ever get smaller. This became known as Hawking's area theorem. It ties black holes to one of physics' deepest laws. The area of that horizon, Hawking argued, behaves like entropy, a measure of disorder that only increases with time. For 50 years, it was a theorem on paper. No one had ever watched a black hole closely enough to check. This ultra-clear signal finally gave scientists away. They measured the 2 black holes before they merged. Then they measured the single black hole left behind after the collision. They compared the horizon area before and after, and the rule held. The final black hole's horizon was larger than the 2 originals combined. Nothing had shrunk. The team called it the best evidence yet that Hawking's area law is real. Stop and appreciate how far that reaches. Hawking connected black holes to heat and disorder. He argued they obey the same deep laws that govern a steam engine or a cooling cup of coffee. And a wave born 1 billion years ago, caught in a tunnel in America, just showed he was right. One collision, more than 1 billion light years away, quietly confirmed a 50-year-old prediction about the nature of space. But the strangest discovery in this catalog was not about a single black hole. It was about a family tree. Here's a question scientists have wrestled with for years. Where do black holes actually come from? The simple answer is that they are the corpses of massive stars that collapsed. But that story predicts black holes should not grow much heavier than a certain limit. Stars in a particular size range are thought to blow themselves apart entirely, leaving nothing behind. That creates a forbidden zone, a range of masses where black holes are not supposed to exist. And yet, this catalog is full of black holes sitting right inside that forbidden range. So the team went looking for another way to build them, and they may have found it. 2 signals stood out, detected about a month apart in late 2024. Both showed black holes spinning unusually fast, with lopsided, unequal masses. Those are the fingerprints scientists expect from what they call a hierarchical merger. The idea is almost eerie. A black hole forms from a merger. Then it finds another black hole and merges again, a black hole built from earlier black holes. A second generation, grown by collision after collision. These 2 events are the strongest direct evidence yet for that kind of cosmic recycling. Think about what that would mean. If black holes can merge and then merge again, they can keep growing. Each collision builds something heavier than before. Do it enough times, and you explain the true giants, the monsters that sit at the centers of galaxies, millions of times heavier than the sun. Scientists are careful here. They say these are likely second generation, not certain. The signals allow it, they do not prove it. But if it holds, it changes how we think the biggest black holes in the universe first grew. One collision is a story, 390 collisions are a census. And that is the real power of this catalog. It is finally big enough to study black holes as a population. For this release, the team analyzed more than 260 binary systems together. When you line them all up, patterns appear that no single detection could ever reveal. Scientists found that black holes do not all form the same way. There seem to be distinct pathways. Some pairs likely formed together from two stars that lived and died side by side. Others were probably strangers, thrown together in the crowded hearts of dense star clusters. One researcher on the team, Storm Columns, described finding separate groups hidden in the data, different masses, different spins, telling different origin stories. A hidden population, slowly coming into focus. The catalog even helps measure how fast the entire universe is expanding. Because each merger reveals its own distance, these events act as what scientists call standard sirens. Hundreds of them together are sharpening our estimate of the universe's expansion rate. That number is one of the great open puzzles in physics right now. Here is the puzzle. Two different ways of measuring the universe's expansion disagree. They have disagreed for years, and no one is quite sure why. Gravitational waves offer a completely independent third method to settle the argument. They do not rely on the old ladders of distance that other techniques lean on. Colliding black holes, of all things, may end up weighing in on the size of everything. So how well can we actually pinpoint these events in the sky? For most of history, astronomy meant one thing: collecting light through a lens. Gravitational waves are different. They are not light. They are the shaking of space itself. That is why scientists describe this as hearing the universe rather than seeing it. A telescope shows you a still picture. A gravitational wave is more like a sound arriving in the dark, and with 3 detectors listening, the team can now locate that sound with new precision. One event in this catalog was pinned to a patch of sky just 6 square degrees across. That is the most precise location ever found for a gravitational wave source. It matters because a tight location lets other telescopes swing around and hunt for a flash of light. When gravity and light are caught from the same event, scientists call it multi-messenger astronomy. We have done it before, and it was breathtaking. In 2017, the detectors caught 2 neutron stars colliding. This time, telescopes around the world saw the flash that followed. For the first time, we felt an event in gravity and saw it in light at the same moment. That single collision taught us where much of the gold and platinum in the universe is forged, in the debris of dead stars smashing together. It is only honest to admit the limits, too. Most of these black hole mergers give off no light at all. For many, we know they happened, and roughly how heavy they were, but not exactly where. The distances carry uncertainty. The masses carry uncertainty. Good science states that plainly. What is not in doubt is the sound itself. 390 times space has rung, and we have heard it. And we have been listening for only 10 years. So, step back and take in where we actually stand. A little over a century ago, a physicist predicted ripples in space-time, then doubted we could ever feel them. For 100 years, they stayed a rumor written in equations. Then, in 2015, 2 black holes that collided more than 1 billion years ago moved a mirror by a fraction of a proton. And we caught it. We had opened a brand new sense. For the first time, humanity could feel the universe move. 10 years later, the tally stands at 390 collisions, and it is climbing 3 or 4 times a week. This one catalog added 161 of them in a single release. It confirmed a prediction Stephen Hawking made in 1971. It found black holes that appear to be built from earlier black holes. And it did all of it by measuring a tremor smaller than the particles inside an atom. Every one of these signals is ancient. Most of them left their black holes before the Earth even existed. They crossed the universe for 1 billion years or more. And they arrived, faint and patient, in our decade. We happen to be listening. That is the awe of it. Not that the universe is speaking. It always was. It is that we finally built the ears to hear it. If this gave you a new way to look up at the night sky, take a second to subscribe. I follow this science closely, and the listeners are only getting better. The next catalog is already being recorded. Until then, keep looking up. And remember, the sky is not silent. We just learned how to listen.